Hello, I'm Elixir, the creator and maintainer of the YOLO object detection library for Elixir. And finally, I've been able to publish the 0.2 release, which I think is a crucial release for this library because it brings three major enhancements, which are, well, you can see here I've written all the different things that this release brings, but there are three major things. Well, first, added YOLOX support, and for this I really have to thank Andrew Pett. And then Model-Agnostic Postprocessing, which is a terrible name. Unfortunately, I couldn't find a better name than this, but stick with me because I'll show you how this feature makes possible to load a new variety of models, like models trained on new datasets and even on your custom dataset. And then major performance improvement, especially in post-processing. And then I've also updated the whole documentation to reflect the new changes, and also updated and added new LiveBooks. So let's start with to see the YOLOX support. Let's start with a question: why? Why having support for another model matters? We already have Ultralytics. It's a great way to explore the library. The models, Ultralytics models, are fast. They have a great tooling to fine-tune the models and great documentation. So, well, first, the library. I thought to write the library. I never thought to write the library just around the Ultralytics models. So, reason why I wrote the Ultralytics implementation around the model behavior, which you can use yourself to bring new models inside the library. You just need to implement the pre-process and post-process callbacks, and you can bring the support for new models or other models in the library. Or probably the main reason why I'm happy to have the support for this library is for the Ultralytics licensing limitations, which could be a problem for some developers and some companies. Because Ultralytics, by the way, you can find this link in the description below of the video. Ultralytics operates under AGPL license with enterprise option. So while AGPL technically allows commercial use, there is copyleft requirements that could create a major barrier, especially for companies. While YOLOX, the license is for, well, code, especially models, is it's Apache license v2, which is far less restrictive. And you find this link if you want to know more about these models, and this is the Python code, and here you also find the link to the YOLOX paper, and obviously here you find the weights of different model sizes, and there is the other cool thing is that here they also give ONNX weights. So we don't have to convert the PyTorch model to an ONNX ourselves. We already have the ONNX format available. So let's see how to load and run YOLOX models. So first, this LiveBook here, you find it in the libraries repo. Under examples folder. So here I'm on a Mac, so I use the CoreML EPS with Ortex. All right. Then, as I said, we don't have to convert the model ourselves. We can just download the ONNX. And here I'm going to use the M version. There are also other sizes. And great, here I've downloaded locally the Nx file. Here I load the traffic image, and it's pretty much here I'm using CoreML, and it's pretty much the same as we were doing before. So we load the model with the load YOLO load function, the model path, and here we pass model implementation. By default it's Ultralytics, and the classes path. The models are trained on Coco dataset, so we have the classic 80 Coco classes, and then the detection, the functions, and how we use the library, it's exactly the same. We just need to pass the implementation, the classes path to the right classes, and that's it. Okay, so we see that we have our output, and exactly the same. We use the here Kino YOLO to draw the detected objects, and it works great as the Ultralytics model in the same example. Now let's see why I'm pretty excited about this feature, Model-Agnostic Postprocessing. So previously the library was locked into a rigid 8400 by 84 model output shape, essentially limiting us to Ultralytics models trained on Coco dataset with 80 different object classes. So we were stuck with exactly 8400 detection candidates and restricted to 80 object classes. This 84 is stands for the coordinates and the sizes of the bounding boxes, and 80 are the probabilities of the object classes. So we were unable to run our custom models trained on our custom data, for example, or other models. For example, like I'll show you in a second, Ultralytics YOLO v8 model trained on a dataset which brings object detection up to more than 600 different classes. This is why it's a big deal for me. So removing this constraint means that we have complete freedom. We can have models that have an output with any detection candidates and any object classes, which means we can run our models and models trained on our data. So we are going to now see a LiveBook here. That is, you can find this LiveBook. It's Ultralytics YOLO v8 Open Images v7. It's a v8 model trained on this different dataset, which has more than 600 classes. So you will see here, I've commented just because I don't want to run some of these cells, but now the Python part where we convert the PyTorch to an Nx is now part of the LiveBook, so you don't have to run the Python script if you just want to focus and have you now have everything here in the LiveBook. So we have our ONNX model, and you also find this this link in the description of this video. You can here you can read more about these models and the performance and the classes. And here we have this image, actually a table with some food. And here we load the model exactly like before. The code is exactly like the same code we used previously. We just use the model path, which is the path to the new model, and the classes path. But the rest adapts automatically to the new model. So this model is definitely larger, so it takes a little bit of time. And here we have, you see, table, kitchen appliance, and here we can render, you see, food, kitchen appliance, table, which I think is pretty cool. Okay, all interesting, but yeah, again, it's another model, a generic model. What about my data? If I want to, for example, detect components in a PCB, on a PCB. So I've trained this model. Again, here I'm going to run the cell where we have our, this is an Ultralytics YOLO 11M trained on some custom data PCB, and I'm not gonna run this Python script to convert the on Nx because I already have the on Nx. We load the model. Great. You see the classes are capacitor, resistor, 2, 3, IC. There are some, I took this data set from the from RoboFlow, and I will publish a video where I show you how to train a model like this. So I don't go too deep on to describe the classes and what they are and where I did find the data set. But here I have a picture. Actually, it's a picture of a monitor. It's a microscope for to better see the PCB. But and you see that what I just did is to load the model, and this is this picture, and I run the model, and it detects capacitor, and the resistors. I think this is really cool, especially because it's really easy to train these models. I had fun, for example, another example, I had fun to train a model that detects resistors, for example, and understands, based on the coloring, understands the resistance value. And yeah, and the code is always the same, just changes the model, and we get this. Pretty cool. The third enhancement is about performance. So when I've rewritten the part of the post-processing to remove this fixed constraint, shape constraint, I've been able to optimize part of the post-processing using Nx.Defn, and I was able to bring quite a big improvement in performance compared to the previous implementation, Elixir implementation. Before, on my Mac, it's a MacBook Air M3, I was able to run with this implementation around the post-processing was about 500, so half a second, 400 milliseconds, so quite a lot. So the reason why I've implemented and also released it's a separate library, FastNMS, which is a NIF, Rust NIF, that brings down the time, the post-processing time to around 2 milliseconds. The reason is that you need it. You need that kind of performance if you want to run these models in real time. But with this, this implementation here, so the default implementation, YOLO NMS, it's really it competes really well with FastNMS, because now same machine, I'm able to run the post-processing, the full post-processing, so filtering and NMS at about around 4 milliseconds. You can run this benchmark here. There are some benchmark NMS here. So here it's the YOLO FastNMS versus the default this Elixir NMS implementation. Actually, it's an implementation with Nx. And the main reason why it's far better is because I've rewritten it. I've rewritten some of the functions using Defn, but I had obviously to refactor a little bit how the data is managed. So what's next? For sure, I'll publish some screencasts around the library, and especially around custom models, so training models on custom data. And probably I'll do it in the next few weeks. So you can subscribe to the YouTube channel or to the newsletter to be pinged, to be notified when these videos are available. And about features. So first thing is, for me, object tracking. I've implemented, I did some experiments. So the idea is to bring a stable release with object tracking, and then multi-framework support. At the moment, the library uses Vortex to load the model and run inference. And it would be cool to support also other frameworks like Axon, or now there is Nx Halo, which means that we would be able to run the models, even our custom models, on a Raspberry Pi 5 with this baby here. It's a Halo 8 and AI hat, and especially running it on nerves. So this is it. So if you want to contact me, just feel free to send me an email or a message via LinkedIn or X, or I'm also on Slack, the Elixir server, and also Elixir forum. So feel free to contact me if you have any issue with the library, or even if you have something to show, or use cases, real world use cases of this library would be great. Thank you. Bye bye.